Okay, today we start talking about the weak topologies. The first section is on the dual spaces. Okay. Okay, we have at least learn about dual spaces when we study real analysis. A typical example for dual spaces for LP, the dual space of LP is LQ, where P and Q are conjugates. Okay, so we actually can generalize this to the setup we have here. When we have a Banach space or even just the B star space, we can define the dual space. The definition is given as follows. Suppose we have a B star space, meaning that we have a linear normed linear space. Then we can define the norm for all linear bounded linear functionals on X as follows. F is a bounded linear functional, and it is defined as the supremum of f of x, where the norm of x is equal to 1. Okay, this is for any f in x star. So f is a bounded linear or continuous linear functional. Then we can show that this and this norm here is not defined as in here. This is actually a Banach space. And it's called the dual space of X. Okay, so sometimes if you like, you can write this as norm star means that is the norm for the for f for the bounded linear functional. Otherwise, you can just write it this way if it's clear from the context. Okay, so that's the definition for dual space. So even if it's just have a B star space, this becomes a Banach space, and then all the results we have for Banach spaces can be applied here for this dual space. Okay. Now let's give two important examples. One is the Drp example I mentioned earlier, and the other one is on the dual space of continuous functions. Dual space of the space of continuous functions. Okay, so first example. For any p between 1 and infinity, let q be the conjugate of p, which means that that means p over p plus 1 over q is equal to 1. And more specifically, that means q equals to, if p is greater than 1, then q is just p over p minus 1, which is also a number greater than 1. And if p is equal to 1, then the q is equal to infinity. Okay? Then the dual space of p, the dual space of LP is the LQ. Okay? Particularly, let's focus on this simpler case where this is the LP space over the interval 0, 1. The dual space of that is equal to it's the dual space, it's the LQ space on this same interval. Okay, so we extend this result soon later, but let's first prove this. Okay, so first of all, it will be easy to show that for any function in here, we can use it to define a bounded linear functional in here. Okay, and then we want to show that everyone in here, for everyone in here, we can find some function here such that the one in here can be used to define the element in here. So you'll see that soon later. But first, we will show that for any element in here, we can use it to define a bounded linear functional for the LP space. Okay. So first of all, by Holder inequality, we know for any function f in LP, so I will just write it at LP since the interval is clear, it's 0, 1. G is from LQ. There is the integral of f times g. We know that is bounded by this, and by Holder's inequality, this is bounded by that, right? And this is just the integral of fp root of p times the integral of g to the q and 1 over q, 0, 1, right? That's all. That's what we know by the Holder's inequality. And also, the Holder inequality tells us when this inequality becomes equality. It holds if and only if the function g is, again, you need to separate these cases. When p is bigger than 1, then the g is the sign of fx, okay, times f of x to the power p minus 1 over the norm of f p minus 1. Okay, so that's for the case p greater than 1. And if p is equal to 1, then we simply define this to be the sign of f of x. Okay, so the equality holds if and only if this g is defined this way. Okay, so that's what we know from the Holder's inequality. And from here, we can see for any g in LQ, we can define this fg. It's a mapping from LP to R, such that the fg applied to any function f in LP is defined to be the integral of f times g. Okay, for any f in LP. And then from the result above, we can see that if you take the absolute value of this scalar from what we have here, this is just equal to the integral from 0, 1 g. And then from the inequality above, we can see that it's less than equal to the p norm of g times the q norm of g, the p norm of f and the q norm of g, which implies that the norm of g is the norm of fg as a functional. The norm of fg is less than equal to the norm of g, the q norm of g. And actually, the inequality becomes equality if we choose the g properly. We choose the f such that the g happens to be like this, and then the inequality becomes equality. Okay, so this is actually, we can replace that by equality. Okay, and this also tells us that the FG is indeed in this way, and the FG is indeed in the LP star because it's bounded due to the bound in here. It's bounded by that. Okay, so what we have shown so far is that any element in here can be converted into, or can be identified with some element in here. So if you have G here, you can define FG in here. So that means this works. Okay, this is true. Now the question is if this is also true. Okay, so in other words, we want to show that for any bounded linear functional defined on LP, say F is a bounded linear functional from LP to R, we want to show that there exists some G here such that the F is just FG. Okay, that's what we want to show. Okay, so now let's see how do we do this. I'm going to do this in 3 steps. The first step is I want to show this. I want first to find out what this G is. Okay, I want to find out what this G is. I want to find out this G such that at least F, when we apply this F to a simple function F, with this F is a simple function in LP, I want to show that this is equal to F times G. Okay, that's the G is what I want to identify. And then if this is true for all the simple functions, I want to show that this is also true for the general functions in LP, any function in LP, not just simple functions. And I also want to show that the norm of F should be equal to the Q norm of G. Okay, so I want to do this several things. So I'm going to do this in several three steps. So the first step is for any F in LP star, I want to find this G function. Okay. So what I want to do is that we define a mapping. We call new. It's a mapping from the measurables, the set of the measurable sets, all the measurable sets to R. So it's just a sigma algebra of measurable sets M over the interval 0, 1 and map it to R. Okay, I define this as follows. The value of any measurable set E is equal to F applied to the characteristic function of E. Remember, the characteristic function here just means that it takes the value 1 if the point is in E, and it's 0 if X is not in E. Right? That's our characteristic function. So I'm going to define my new as a mapping like this for any measurable sets. Yeah. Okay. And now I'm going to show that this new is a signed measure. Okay, hope you still recall what the signed measure is. We can first show that we use this new to evaluate to measure empty set. It is 0, and that is clear from the definition here. If I put 0 here, this is just giving me 0. So since f is a linear functional, I'm applying f to 0, and I should get 0. So that's okay. Okay, and also this new should be finite because no matter what value I take, I will get some real number, right? No matter what set I take, this is going to give me some real number because this f is a bounded linear functional. Okay, for any given E should give me some real value. And the key here is to show that this new is countably additive. Okay, since I want to show it is a measure, signed measure. It needs to be countably additive. Okay, remember what the countably additive is. Suppose we have like this E1, E2, a sequence of sets which are mutually disjoint. Then we need to show that the new on the union of this is equal to the sum of nu on each of them. Right? That's what we need to show. So we need to show that this is true. Okay, so how do we show this? So the right-hand side actually can be written as, say I take the sum, a finite sum first, up to some k. And also for the others, I just put all the others together. So let me write in this way. This is equal to the nu of the sum from 1 to k for ei, then nu of I from k plus 1 to positive infinity, and for ei. Okay, so I know this because of finite additivity. Right? I just split this infinite sum into two parts, a finite sum part and the tails. Because the new apparently is finite additive, since you can easily see that from the definition. If I have two sets, E and F, which are disjoint, then the new E, the new applied to E plus F is new E plus new F. Okay, that would be easy to show, and this is like the E, this is like the F. So that's true. And then because of the finite additivity, I know that this is equal to that plus nu of this union for k plus 1 to positive infinity and ei. Okay, so from here to here, the only thing is that this is replaced by that, and that's true because of the finite additivity, and then this is kept. Okay, but the question is, do we have this equal to this? And if that's the case, so if this is true, then if that's true, then we go from this route to show that this equation actually holds. Okay, the question is if this holds. Okay, to show this holds, we just need to show that this part goes to 0 as k goes to infinity. Okay, that's the only thing we need to show. Okay, let's see if that's true. So let's denote the dk to be the union of this sets. Okay, let's decay uk in this way. Then we can see that this is what we're trying to show, right? We want to show this goes to 0 as k goes to infinity. So on the one hand, we know that this is just by definition is f of that. Okay, and f is in LP. So apparently this is in LP, and f is in the dual space of LP. So that means this should be bounded by the norm of f as in the dual space of LP times the norm of this, where this is treated as we said, this is treated as some point in the LP space. Okay, but by definition, we know that this is just equal to, it's just that dk, right, d mu 0 to 1, and this needs to take the p's power and then 1 over p. right? So if you like it as the p norm, and apparently this inside here is just going to be 1. It's still the same characteristic function because it takes the value either 1 or 0 and take the power is still the same. So what I have here is just the standard Lebesgue measure. So this is the mu of decay. Okay, so what I showed so far is that the mu of decay is bounded above by the norm of f, which is a constant, times the piece root of this measure, the Lebesgue measure of decay. Okay, now let's go back to look at the decay. Well, apparently the decay is decreasing, right? Because decay defined in this way, so when the k gets larger, we're taking the union of fewer sets. So the decay is actually decreasing, and it's going to empty set, right? As k goes to infinity, it goes to empty set. And also the decay itself has a finite measure because we're considering all these sets in 0, 1, right? They're all in 0, 1. So the measure of decay is finite. So by the continuity of the measures, I know that this one goes to 0 as k goes to infinity, right? Since the mu of decay is finite, the decay goes to empty, so the mu of decay goes to the mu of empty set, which is 0. So this whole thing will go to 0. Okay, and that shows that this thing, which is this is whatever decay is, this one goes to 0 as k goes to infinity, and that completes the proof here. And then we complete the loop, which means that this is actually equal to that, and the countable additivity is true. Okay, then we can also see that from the same proof, let's say that if mu e is equal to 0, then the nu of e, as we showed here, you can even take an absolute value if you like, is bounded by the norm of f times mu of e to the power 1 p. And again, you can see that this is just equal to 0, and that implies that nu e is 0. And this implies that the nu is absolutely continuous with respect to mu. And therefore, by the Radon-Nikodym theorem, there exists some measurable function g such that, so this is the measurable, or mu measurable, such that the nu e equals to the integral of g over the set E for any mu measurable set E, which is M. Okay, so this is true for all the measurable sets E. Okay, so here, this is how we got this G. We got some function G, and so for any function f in here, I found some G in here. I haven't showed that is in here. I just showed that there exists such a G. So I also want to show that this G is actually in that set. But at least that we found some G, some function G. Okay, so from the proof above, we can see that the nu of E is equal to the integral of that. Okay, or in other words, this is equal to 0, 1, the characteristic function of E times G, d nu. But on the other hand, we know by definition, the nu of E is equal to the f of characteristic function of E. So you see the similarity that if this is not a characteristic function, is some general function f, then we're done. Okay, we prove that this G is what we wanted. At least this G can be used to identify or can be used to characterize what this bounded linear function f is. But so far we only show that it's true for characteristics of a function. But because of the finite additivity, we can easily extend this to, we can easily show that this is also true for simple functions, because simple functions are simply finite summation of characteristic functions, weighted summation of characteristic functions. So at least we can show that is true for any simple functions. Okay, so this is what we're going to use in the next. Let's finish our first step. We found some function g, but we also want to show that this g is in LP, is in RQ, and also this g makes this hold for any function f in LP, not just simple functions. Okay, so we first show that this g is in RP. Sorry, this g is in RQ. So we want to show that the Q norm of g is actually finite. Okay, so let's see how to show that. Okay, we're going to separate the discussion into two cases. The first one is for p greater than 1. Okay, so if p is greater than 1, then for any t greater than 0, we denote the following. We define the following set Et, which is defined to be the set of points where let's just say the g is less than or equal to t. Okay, so remember that this is some subset here at 0, 1. Okay, that's one, and the other one is that I'm going to define the function f to be the characteristic function of this et, and then the g q minus 2 times g. Okay. So remember that in this case, if I take the absolute value of f, it becomes the characteristic function of g, and then g to the power q minus 1. But because q is greater than 1, so I'm taking the q minus 1's power is greater than 0. This is greater than 0. So it doesn't matter what this g is. Even the g is 0 is okay. Okay. So from here, we can claim that, I'm going to claim that the f applied to this function f is equal to the integral of f and g. Okay, this is what I'm going to claim. Well, we already showed that this is true for simple functions as above. Right? We showed that this is true for simple functions. But right now, this is not a simple. This is not necessarily a simple function, right? So why this is still true? Well, you can think in this way. Because we have a specific function f defined in here, so I'm going to get a sequence of functions fk, a sequence of simple functions fk, such that let's say that the positive part of that converges to the positive part of f. Okay, so these are simple, and the positive part goes to the positive of that, and also the negative part also goes to the negative of f. Okay, so you can imagine in this way, if f is something like that, so your simple function is like this, the first simple function maybe look like this, and the next one is going to be refined, and it's getting closer to the f. It's still simple, but it's getting closer. Okay, it's like it looks in that way, and then we can see that we can also make sure that this fk's, they are simple function. I can also make sure that the fk's are in RP. Okay, so to prove this is that let the fk be simple functions in LP such that on the one hand the fk plus or minus goes up to f plus minus, and also the fk convert to f in the LP, because these simple functions are dense in LP, so we can always use that to converge. And also we want to get the monotonicity so that we can apply bounded convergence theorem or dominant convergence theorem later. Okay, so from here we can see, on the one hand, we can see that f of fk will converge to f of f. The reason is fk converges to f in LP, and this f is in the dual space of LP. It's a bounded linear functional, so it's continuous. This f is continuous. That's why this is true. Okay, but on the other hand, we can see that the integral of fkg. So let's look at fkg. Fkg, according to our definition, the f is like that. Okay, and if you multiply the fk by g, and they will convert to f times g, which is, I should say, will go up to f times g, which is equal to this times the gq, right? Because f is this, and then you multiply another g, then this 2g gives you the g squared, and combined with that, you just have g to the power q, and this is a positive, non-negative function, so this goes up to that. So I have a sequence of simple functions. I can it's monotone converging to that. So that's why we have this converging to the integral of fg, and it is just as we said, just that. Okay, and this is by the Bethe-Levy. Which is the one we use to prove the dominant convergence theorem. So we know that. Now we know that for simple functions, these two are the same, because we show that this is true for simple functions fk. So that's the same. And this is the same means that these two are the same. Okay, and that is how we showed this one, this claim. Okay, so that's how we then can use this fact here to continue. Okay, that's what we have. I want to show this, continue. So how do we continue with that? So we first verify that the integral for f and g, right now, as we said, it is equal to chi of et times gq. Okay, and this is just taking the integral of g to the power q over the set et. Okay, so on the other hand, we also know that if we take the p's power of f, the integral of p's power of f, the f is this. So this is just the et. You see that et, and then the g to the power. When I take the absolute value, then I have the power q minus 1. And then I take another p's power. So that's the product of the two. But remember that the p and the q are due to each other. So the p should be, q is p over p minus 1. And p is also q over q minus 1. So that's why the p times q minus 1 is just equal to q. So that's just the g to the power q for the et set. Okay? And now from here, we can see that the integral of et for the gq, and that is the first line above, which is equal to the integral of fg. And by the claim we made earlier, we know that this is just equal to the f of f. And from here, we know that it's bounded by the norm of f times the p norm of the little f. But remember, what is the p norm? So we know that. We know this. 1 over p is this. 1 over p is this. 1 over p. So this p norm of f is nothing but just the q norm of, it's just this. Let me just repeat it in here. Et gq 1 over p. So now I have this to the power 1. I have this same thing to the power 1 minus p. So I divide this on both sides. I will get the tgq. So it's 1 minus 1 over p less than or equal to f. But remember that 1 minus 1 over p is just equal to 1 over q. So what we showed is that the integral of that, so power 1 over q, is less than or equal to f. Okay, so everything here, the g is bounded. G is defined over the ET, but we said that the ET is for all the set, is the collection of points which is bounded by some t. So everything we have below works, okay? Because we're working on the function g that has a upper bounded by t. So this is true, but when we make t tend to infinity, this is still true, right? So as you can see here, if t gets larger and larger, say I take the t to be natural numbers, it's getting larger and larger, and eventually this will go to extend to this set. So when t goes to infinity, as t goes to infinity, the et tends to 0, 1, and this is still holds for every t, and this just means that the g q norm of g is bounded by f. Okay, and now we can see that is the q norm of g is actually a finite number, and that means the g is actually in the RQ space. Okay, so we finished the second step. We showed that the function g we found earlier is actually in RQ. There's one more thing to show. We need to show that this is equal to fg for any f in RP. Previously, we only showed this is true for simple functions. And we actually extend that a little bit to show the claim here, which is not simple. But right now, we want to show this is true for general function, any function in RP. Okay, and this becomes easier since we have, sorry, it's the third step. This becomes easier since we have the boundedness of G, or this one here. And why is that? The reason is, if I want to show this is true, we first, again, let this sequence of simple function fk to convert to f. This is simple. So we let this convert to that in the LP space. Then, again, according to, let's just look at the f of fk minus f of f. So, by definition above, this is just let's just say this. No, let's say this in this way. Let's look at the f of fk minus the integral fg. Okay, by definition, the f of fk is just integral of fk g minus, and then I just repeat here. Everything is from 0 to 1. The integral is from 0 to 1. I will just ignore those. So this is less than or equal to the integral of fk minus f times g, right? And then by Holder's inequality, this is just the fk minus f p norm, p norm, and this q norm. And this is true because fk and f are all in LP space. G is in RQ space, so that's why this is true. And then this is bounded by the norm of f, because that's what the bound for the q norm of g is. Right? Then we have this. And if fk goes to f in LP space, then this goes to 0. Okay? So that means the f of fk, so this converges to integral of f g. Okay, but on the other hand, I know that this also converges to that because fk is converging to f in Rp, and f is the capital F is a bounded linear or continuous linear functional. So that's why this is also true, and that's why these two are the same. Okay, and we didn't specify what this f is. It can be any function in Rp. This is true. Okay, so that completes the proof. Okay, so let's look at, so that's the example that you need to be, you probably need to be, have very deep impression. When you have the Lp space, then the dual space will be Lq. And this can be extended to not just 0, 1. It can be, say for example here, it doesn't have to be 0, 1, because we can always do this for a sigma finite set. It means that the omega, say I have a measurable set omega, which is sigma finite, meaning that it can be written as the union of k's from 1 to infinity, and each one of them, they are disjoint, and each one of them has a finite measure. Or they don't have to be disjoint, but we can make them disjoint from each other, and then the same thing applies to each one, each ek, and then just repeating this on each part, each ek, and then we can paste them together to get the same result for the general space. So that means, in general, if you have omega m, and you have a mu, so this is just a sigma finite. And then we have the L omega, okay, which is the, say Lp omega, which means all the functions f such that when we do this, it is finite. This is what Lp omega is. Just a set of functions from omega to r, such that the integral like this is finite. Then the dual space of this becomes Lq of omega. Okay, so we can actually extend this result to a more general case. Okay, so that's the example here. Okay, so that's one example, which we have just partially know that in the real analysis class. Now I'm going to show you another example about the dual space of the set of continuous functions. The dual space of C01. Okay, so this is our the continuous set of continuous functions defined over the interval 0, 1. And the dual space of this so first you can imagine if the dual space is going to be something larger than the Lp space or not. We know that this is a subset of L1, 0, 1, right? This is a subset space of that. And we know that the dual space of L1 is L infinity, as we showed earlier. Did I show? Yeah, sorry, I forgot to show that. Sorry, here I only show that this is for P in greater than 1. I haven't shown that for, this is true, also true for P equals to 1. So sorry, I should do that. Okay, let me postpone this a little bit and show that. Okay, that was still in step 2. Sorry for that. Still in step 2, and I want to show that the G infinity norm is bounded by F for P, when P equals to 1. Okay, because when P equals to 1, Q is infinity. Okay, so I want to show this. To show this, let's first consider, say, for any epsilon, let me define the a epsilon to be the set of points where the g is greater than or equal to the norm of f plus epsilon. Okay, as you can see, the goal here is to show that a epsilon has a measure 0 for any epsilon. Okay, if that's the case, then we finish the claim here. Okay, and to show that, we again let this f to be the characteristic function of et. Et is the same as before. The et for any t greater than 0, I define et to be the set g is less than the set of points where the value of g is less than or equal to t. Okay, I'm going to take this intersection of these two. Okay, so I'm going to take the intersection of these two, then times the sine of g. Okay, so this is going to give me some value, either 1 or 0. This is giving me value either 1 or 0 or negative 1. Okay, but so we can see that the product of the two must be either negative 1 or positive 1 or 0. So it has to be in L in L1. Okay, and also then we take the integral of this f, take the absolute value of that. This is just according to our definition above, this is just giving me the measure of et and a epsilon. Okay, so that's what we know on the one hand. On the other hand, we also know that we apply f to this. This is going to give us this. Okay. Again, we'll see a similar issue as before. This is not necessarily a simple function. This is a nice function, but this may not be giving us a simple function since the sine, well, it could be, may not be a finite sum of measurable sets or characteristic of measurable sets. So, but we can still use the same trick. We can use a simple function to approximate this. This is in R1. Okay, so we can still get that same claim as we claimed before, using the same proof for the claim before. And this is true. But on the other hand, we know that we multiply the f and g together. This is just giving me the chi of eta epsilon and the sine of g times g, which is giving us that, right? So we know this, and this is just equal to t epsilon g. And according to our definition for a epsilon, over this set, the g will be greater than or equal to this value. Okay, and then times the measure of the set of the set that we're taking integral over. Okay, that would be this. So epsilon. Okay, so now what do we have? We know that this, on the one hand, this non-negative, this also non-negative. We know that, and this is equal to the f of f. And we know that this is bounded by that times f1. Okay, but f1 norm is this. So that's just equal to the f times the measure of eta epsilon. Okay, so now let's collect what we have. We show that this is less than or equal to this. But apparently this is some number strictly bigger than, strictly smaller than that. So if this right hand side is even bigger than left hand side, the only thing we can do is that, the only thing we have is that we can claim is that et epsilon, this is going to be 0. Okay, and now when t goes to infinity, the et goes to t going to infinity times at the et goes to the whole interval, and we still have that with the mu of et is always, sorry, it just implies that the mu of a epsilon is equal to 0. And as we said earlier, this is what we wanted to show. For any epsilon, we want to show that the measure of a epsilon is equal to 0, because this will imply that. Okay, the essential upper bound for the norm of G is just equal to f. Okay, or the set of points where the G is greater than or equal to f has a measure 0. Okay, so that completes the proof above. Okay, so I missed this part, but you should add this when the p is equal to 1. And the rest will be the same. The step 3 is identical as before, so we don't need to repeat that. Okay, so now let me continue with where we left over. We want to show that the due space of C01 is this. It's the B-wave space. It's slightly different from the B-wave space we understand earlier. It's just a wide trivial change. It's a set of functions f. It's going to be the set of functions f where it's a function, real value function from 0, 1 to r, such that the f0 is equal to 0. This is the only thing we require. And the TV norm is bounded. Okay, that's all the due space. I didn't finish with what I said. We know that this is in L1. Okay, and then we know that the due space of L1 is L infinity. Okay, do we expect the due space of that to be smaller than this or larger than this? And the answer is the due space of that should be larger than the due space of this, or it should be larger than that. The reason is this is a smaller set of that. So to get a bounded linear functional for a smaller set is easier, right? So that means we could have more candidates as a bounded linear function over that. That's why we should have a larger space. Okay. But anyway, that's the actual due space of that's the actual due space of the C01. Okay, so let's show that this is true. Okay, recall, yes, you still remember, recall that TV norm of f is defined to be the supremum. So what we do is that you can have the 0, 1, and you can make partitions. This will be T0, and then T1, T2, so on and so forth, up to the T, whatever you have, the Tn, which is the 1. And then we call this a partition, which is the T0, all the way to Tn. That is equal to 1, that is equal to 0. So on each interval, you take the absolute value of Ti minus T, or I should say, for each partition, you can take the sum for I from 1 to n, where on each interval you take the value of function at the right endpoint minus the left endpoint. Okay, then the TV is just a supremum of this. Okay, we saw that this is actually a norm, or semi-norm. But right now, since the f of 0 is 0, so this is actually a norm. Okay, this is actually a norm over this B-wave space. Okay, so you need to show this. It's a norm. Actually, you want to show that the BV01 defined here with this norm is a Banach space. Okay, so we first need to show that this is the Banach space, just based on the definition here. So you just need to show that it's a norm. This is actually a norm, and also the space is complete under this norm. The idea is that to show its norm is pretty straightforward. Just use this property to show the three conditions for a norm, and then to show it is complete, you get a Cauchy sequence in here. Say you have fk, which are Cauchy sequence in that. Then you want to show that, say for example, you have to show f of k minus f of j. Say this goes to 0 as k and j goes to infinity. And then you first want to, I think this is something we have done several times at the beginning of the class or very early of this class. We want to first find a limit of the sequence at each fixed point. So for each fixed point between 0 and 1, we want to show that f of k at t convert to something, and this thing is going to be defined to be f of t. Okay, and to show that is true, you need to use this norm here. Okay, so to show that it's pointwise limit for the sequence fk of t for each t, and then show that this fk actually converges f using this TV norm. Okay, so it's not really difficult, and something that's something similar to what we have done to show completeness. So I'll leave this to you as an exercise. So that's the first thing we need to prove. It's a linear space. It's a norm space. Actually, this is Banach space. The norm is complete under this norm. The second thing we're going to do is to actually show that any function f, or you need to show that the dual space of the C, so dual space of that is equal to this. Okay. To show this, let say x be any point in that, and then for any f in the BV space, let's consider the Stelges integral. Okay, this is very similar to the Riemann integral, but we define this for this function f. So when we write it in this way, it means we say we have some partition of the interval 0, 1, like before, and then for each partition, we take the x of x ti star. So this is like the interval ti minus 1 ti is just one of many segments in between 0 and 1 for our partition, and then the t star is somewhere here. Doesn't matter where it is, just anywhere in between here. It doesn't matter because the x is continuous. So when the interval is getting smaller and smaller, this should be, it doesn't matter which point you choose, times f of ti minus f of ti minus 1. Okay, and take the sum and then take the limit where the segments goes to, the length of the segments goes to 0. So the delta is defined to be the maximum of ti minus ti minus 1 for the specific partition. Delta. Okay, that's the definition for delta. So delta goes to 0, and that's our definition. Okay. So if we define this in this way, then we can show that for this f right here, we can define this as a mapping from C01 to set of real numbers where it takes any x and map it to that, and that is defined by the Stelges integral. Okay, and definition is above. Okay, so now we want to show that for this f, which is defined out of this f, it's a linear and is bounded, or linear and is continuous. It is a bit obvious that it's linear, right? And we just need to show that it is also a bounded functional. Okay, and how do you show that it's bounded? Let's see. We'll apply this to x. Then we can take an absolute value, doesn't matter. Then this is equal to the integral of that. Okay, so according to our definition, for this integral is defined in this way, right? So now let's just look at for each specific partition, I can see that this times f of ti minus f of ti minus 1, if we take the absolute value of that, and apparently this is going to be less than or equal to the sum I from 1 to n, and this I take the absolute value of that and then take times the absolute value of this, so it's just a it's just normal of x, sorry, normal of x, I'm having the star there, times the absolute value of f of ti minus f of ti minus 1. Right? I can pull this out, it doesn't matter because, sorry, you can pull this out because this is just a constant. And then for the rest, it will be bounded by the TV norm. So this is always bounded by the norm of x times the TV norm of that. Okay, and this is true for any partition. And you take the supremum is still true, so this is always less than or equal to the norm of x. This norm is in the C01 norm, so you can, if you like, count this. So norm of x is the maximum of xt, where t is between 0 and 1. Okay, this times the f of t. And because of that, we can see that this is not just linear. Linear is pretty easy to show. It's not just linear, but it's also bounded. That's why for any function f in this space, we can define this, and that is a bounded linear functional. Okay, and now finally we need to show that for any function in this space, we can find, sorry, for any function in the due space of that, for any function in here, we can find some point or find some function in here such that this functional, which we call f, is nothing but just this ff for some little f in here. Right, that's the last step. Okay, how do we show that? So for any, again, for any f in the due space of this, we want to show that there exists a unique f in BV01 such that the f is just equal to f. Right? That's what we wanted to show. Well, to show this, let's first think about the set here. Okay, so this is we're going to find the f is on the due space of that. So what this space is, this is a linear subspace. It's actually a linear subspace of that. Right? Apparently, it's a subset of that. And actually, the norm we use is the same. It's also the infinity norm, right? Because that's for definition here. This is the norm C is actually for continuous functions. Is this? But it's just the definition for the infinite norm. our infinity norm. So this is a linear subspace of this. Okay, it's a linear subspace of our infinity space. And now we have a function f that is in the dual space. So that means f is in the dual space. So it's a bounded linear functional. At the same time, we know that for any x in C01, we know this is bounded by the norm of f times the norm of x. Right? This is the infinity norm. So I can define this to be p of x, which is the sublinear functional, because it's just some positive number times the norm of x. So it's a sublinear functional. And this sublinear functional is defined over the whole space. So now I have the f that is from 0, 1 to r, and is a bounded linear functional. Okay, and also have the p, which is defined over here to r, and is a sublinear functional. And I will also have the f that is bounded by p on this linear subspace 0, 1. So all these things imply, by the Hahn-Banach theorem we showed before, this implies that there exists an extension of the f, which we call the f tilde, that is defined, that's a bounded linear functional over the whole space. Okay, and it's also a bounded linear functional. And this f is also bounded by the p. And moreover, if we restrict this f to this linear subspace, it's just the same as f. And the norm of this f as a linear functional over this space is equal to the norm of this f. Right? That's what the Hahn-Banach theorem told us. Okay, and we're going to use this f tilde to help us finding this little function f. And what this f is, this little f is, I want to find this f in the BV space. Okay, I'm going to define my f to be in that way. So if s is already 0, then it has to be 0. There's no choice, because that's the requirement for any function in this BV space. But if s is bigger than 0, less equal to 1, then I'm going to define this to be f tilde applied to the characteristic function of the interval 0 to s. Okay, so obviously this is in L infinity, since it's just the maximum value is 1. And this f tilde is the bounded linear functional on that, so that's going to give me some value. Okay, that's how I define this little f. And I'm going to show this little f is actually, so we need to show that this little f is actually in the BV space we wanted earlier. The TV norm is bounded by the f, which means that, well, this is the part of showing that, right? We need to show this is true, and also f of 0 is 0. That is obviously true as our definition above. And moreover, we wanted to show that f of any function x is equal to the integral of this. Okay, and this is true for any x is C01. We want to show this, and that means this f is just a fg. FF. If this is true, that just means that. Okay, so that means for any f, we found this little f such that this is true. Okay, so that's what we want to show. This is the one thing, this is the one thing, and then this thing. Okay, f0 is 0. This is true. Okay, we're going to show that. Let's show this one. Okay, to show this is true, let's look at any partition. For any partition delta, we know that it's just a partition of the interval 0, 1. For any partition, we can see that, okay, let's define the lambda I to be the sign of this value, it's f of ti minus f of ti minus 1. So this is the f is what I already have. So on each interval, I can see I can take the sign. So it's either positive 1 or negative 1 or 0 over the interval, or over this segment. Okay, then you can see that we take this f of, well, ti minus f of ti minus 1. This is a part of, we take the limit, this will become the total vibration, right? But for any specific partition or any fixed partition, we have this, and that's by definition, it's just lambda I times the f of ti minus f of ti minus 1. But by definition of this little f, it's just the characteristic function. So it's just the sum lambda I, so the f tilde c of 0 ti minus f tilde of c, the characteristic function minus 1. Okay, right? And because of the linearity, we can see that this is just so right here, the difference of that two. Finally, take the difference of that two. That's just don't need this. The characteristic function from ti minus 1 to ti. And then I have lambda I outside, so that's just equal to, sorry, just f tilde sum of I from 1 to n lambda I, the chi of ti minus 1 to ti. Okay, so that's what we got, because the f tilde is a linear functional. Okay, and then from here we can see that this is bounded by the norm of f tilde times the norm of this, which is the infinite norm of this. So the infinite norm of that. But what this one is nothing but just 1. This thing is just equal to 1, because you can see the lambda I is a sign, so it's either positive 1 or negative 1. The characteristic function is just a sum of non-overlapping characteristic function of non-overlapping sets. So that's why this is just equal to 1. And this one, because of the Hahn-Banach theorem, we know it's just f. Okay, so what we showed is this is for any partition, this is less than or equal to f. So if you take the supremum, it's still less than or equal to f. And that is why the TV of f is less than or equal to the norm of f. Okay, so that finishes the second part, this first one here. And finally, we want to show this, the third one. Okay, to show this third one, for any x in C01, remember that the x is a continuous function. So it's continuous, that means uniformly continuous, since 0, 1 is a compact set. Okay, so we can make, so there exists a partition such that the segment are so small. So for any epsilon, I should say for any epsilon, I'm going to add this here. For any epsilon, I'm going to find this partition such that the x of t minus x of ti is going to be smaller than or equal to, bounded about by this epsilon over 2 times the norm of f. Okay, so this is a possible. This is true for any t, ti in the interval ti minus 1 to ti, and for any I from 1 to n. And as I said, this is true because the x is uniformly continuous. So when we make the partition small enough, then we have this. Okay, so that's one thing. The other thing is remember the definition for the Stieltjes integral above, right here. Okay, because this is a limit for this. So that means when this delta, the determinant is close to 0 enough, we know that the difference between this one and this one should be arbitrarily small. So that's also another criterion for me to find this delta. I want this delta to be refined, so refined such that the integral xt dft minus the sum I from 1 to n xti, I just choose di, it doesn't matter, as we said, minus f of ti minus 1. This should be less than half epsilon. Okay, both of them require the partition to be so refined. So I just, if I have some partition delta 1 for that, I have partition for delta 2 for this, then when I take the union of those, it gives me the most refined partition that make both of these two inequality hold. Okay, so I can make this true. I can even make this. Doesn't matter. So from here, we are going to claim, make the final claim. Before that, I define this x delta according to the partition above. It is defined to be psi from 1 to n, and the x of ti is actually this one here. F of ti minus f of ti minus 1. Okay. And also plus x naught. This doesn't really matter, so let me just remove that. It doesn't matter. So I have this. Then I look at the f of x minus 0. I want to show this is these two are the same, right? Now I look at the difference between them. Okay, and this by triangle inequality, this should be less than or equal to f of x minus f of x tilde of x delta. So because x delta is defined in this way, so it is it's in R infinity, right? So it's in R infinity. So that's why I have to use the f tilde plus f tilde of x delta minus this difference xt dft. Okay, so now this part, I know that it's going to be less than half epsilon as we showed earlier. And how about this part? This part is going to be less than or equal to the norm of f, because this is just f tilde, since f tilde is equal to f when the x is continuous on the sublinear, a linear subspace C01. So these two are the same. So that's why this will be the tilde norm. But this is actually just the norm of f. Okay, so it doesn't matter which one it is. And then this, it will be x minus x delta. Okay, and then you can see that the x delta is defined in this way. So when I look at the difference between sorry, I should write this wrong. This doesn't make sense. So I'm going to rewrite this. So this should be our infinity function. So I'm going to define this to be that the x of ti. This is just a number, and then the characteristic function from ti minus 1 to ti. Okay, and we will define it this way. So that is in L infinity from 0, 1. Okay, so now I get that. And why this? So let me write it here. So this first one, as we said, is going to be less than or equal to the f norm times x minus x delta, plus this f tilde x delta minus this still just integral. Okay, and then let's look at the x minus x delta. According to our definition above, this is going to be, remember that the f, this is 0, 1, and make it a partition, and then I have a continuous function. So that's my x, xt. And x delta is that on each segment, I'm just taking the right endpoint, just like that. Just taking the right endpoint. That's my x delta. Okay. So we know that these two are close enough since I chose this segment so small, so that on each segment, it doesn't matter what this x tilde prime is, the difference is always less than that. So that's why on each segment, I choose any t and t prime to be the right endpoint. That will be our difference in here. Okay, so this is actually less than epsilon over 2 times the norm of f. On each interval, then take the sum, will be still less than that. Okay, right? So on each interval, the difference of this is less than that. So over the not the sum, so the maximum of this is still less than or equal to this. Still less than or equal to this. And the other part is this f tilde. So the f tilde x delta, according to our definition, that's just the f tilde of this sum. It's ti, chi ti, sorry, x of ti. X of ti times the characteristic function of ti minus 1 to ti, the interval here. Okay, and because of the linearity, this is just a constant, and so it's a linear combination of those functions. So it's just the sum of I from 1 to n xti. You should use x more different from the chi. Ti, and this chi f tilde of chi is just remember that this is just the f of is f of ti minus f of ti minus 1, according to our definition for the little f, right? So that means this is essentially just this part. So this part is essentially just this part. And I know that the difference between that, which is now our f tilde of x delta, is not far from this. And this tells me this is exactly the difference here. That's how I can claim that this is less than half epsilon, and this is less than the f norm times epsilon over 2 norm of f. But we know that these two are the same, so they can cancel. So that's how I got the 2 half epsilon. From there, it is less than epsilon, or it's equal to epsilon. But now the point is that for any epsilon, we show that this is less than or equal to epsilon, so that's why these two are actually the same. Okay, that completes the proof. So we show that the f of x is nothing but just that. And this is just this of x for any x. And that shows that the dual space of C01 is just that BV01. Okay, dual space of this is just this.